the expectations for AI have shifted wildly back and forth. But the AI winters are generally like the expectations are like, wow, we're going to have robots that can do anything. Human level intelligence is right around the corner, and then nothing changes, and then the expectations like we're not going to invest in it, or it's never going to happen. And this is the closest we've come to generalizing the human ability for learned expectation. That's what we're doing here. And if you think about what toddlers have to do to get learned expectation to be able to not fall, climb up on the sofa and walk and not fall, it's going to take about 2 years before you're still pretty nervous about them doing it. And that's a lot of data, and it's highly specific to your environment. And yeah, they're building multiple models in their head, and we don't have the ability to build these multiple models. There are people working on spatial perception where they're trying to tie these things together, but it is very challenging.
Welcome to the Conversations on Applied AI podcast, where Justin Grammons and the team at Emerging Technologies North talk with experts in the fields of artificial intelligence and deep learning. In each episode, we cut through the hype and dive into how these technologies are being applied to real-world problems today. We hope that you find this episode educational and applicable to your industry, and connect with us to learn more about our organization at appliedai.mn. Enjoy.
Welcome, everyone, to the Conversations on Applied AI podcast. Today, we're talking with Erik Beall. Erik is an imaging AI scientist and product developer. Erik is the CEO of Thermal Diagnostics, where he has developed the Fever Inspect, a thermal imaging-based product that helps keep us all safe by providing accurate, reliable, and foolproof fever detection. He's also a computer vision scientist at Digilabs, where he's using AI for various applications for autonomous ground robots with Rover Robotics and other Digilab companies. Erik holds a BA in physics and chemistry from St. Olaf College, a degree in business administration and management from the University of St. Thomas, and a PhD in physics from the University of Minnesota. Thank you for being on the program today, Erik.
Thank you, Justin, for having me. I really appreciate this, and I've enjoyed the Applied AI meetups that I've made it to over the last few years.
Well, I'm glad you're willing to be on the program today and share some of all of your experience that you bring to the table here. And I just, I highlighted a couple of things where you're currently at today, but I know you've got a long history of working in this whole space of computer vision and AI, and with your degree in physics and chemistry and stuff. Maybe walk us through a little bit in terms of, help us connect the dots in terms of how you got to where you are today.
How much time do you have? Just kidding. I had a really very fortunate series of introductions to technology over the years. So when I was in graduate school, I worked on a particle physics neutrino oscillation experiment. We were firing neutrinos from Fermilab near Chicago to a mine in northern Minnesota. And so I ran the slow controls, the detector control system, because nobody else wanted to. And I was just a grad student where they just give you a bunch of code and tell you to swim. They had a base architecture idea, sketch of all the components, how they were supposed to be. You have to mount it all 1,500 high voltage controllers, magnets, and everything. And I just completed this thing called Linux from scratch, where you build up your own Linux operating system. It's 2000, which I highly recommend. Anybody who's in this field, go through Linux from scratch. You won't regret it. You'll learn so much about the deeper workings of how an operating system gets started up. And I had to build all these different subsystems in C, C++, Python, even Visual Basic for a SCADA interface to the magnet controllers.
Wow.
Piping all this into a raw MySQL database. All of this was compiled from scratch on the various servers because there's no guidance.
Uh-huh.
And displaying web detector control status so the people at the control room could see it. They were all run by cron jobs. This is all pre-Web 2.0. Now you can pull in services that'll do all of this for you. But at the time, we would put stuff in a CVS repository, and it was not the most maintainable code, I would have to say. Learning how to code well is a late skill that I really wish I'd learned earlier on. But that's how I got my introduction. And then I went and did neuroimaging for 10 years at the Cleveland Clinic, where I had a great mentor, Mark Lowe, who taught me methods development. Methods development is not talked about much, but it's sort of the area of science in a field where you're trying to figure out, okay, the way we're doing this, how do we know what we know is true or not? How do you tell what you're seeing from a mirage? Because most of the time it's a mirage, and most of the time those mirages are self-generated. If you start out putting together a study, what do I want to believe? Well, that's probably where you're going to find in the end, by hook or by crook, your mind will just do that to you. So you have to be really careful with your methods. And so that was really very fortunate training, forced me to think more carefully about what I was doing. But that transitioned to taste of business development with head motion tracking, which was frustrating because I was trying to do it from within the clinic. But that led me to look outside the clinic when I started that Kickstarter while I was still at the clinic. So my last 2 years there, I was working on developing this thermal camera system. And ultimately that funded just as we were moving back from Cleveland to Minnesota. And I spent about 1.5 years with a small team, Romania, Cleveland, and here, working on developing a quad-core ARM processor system that run computer vision algorithms on the GPU of the system. And we ran out of funds, and we also lost 2 key components that would have required like $1 million minimum order quantity. So we cashed it about, and I ended up doing consulting for Digilabs and various corporate development projects. That's where I am today. I'm still most of the time working out of Digilabs, and they still support me, but I've also worked for Cognella, an autism diagnostics company, Wärtsilä, an engine manufacturer in Finland, a Fluke Thermography's division, and then my own thermal imaging company making the fever detection device is all going on the shelf.
Interesting. Wow. Sounds like you got your hands in a lot of different stuff. I mean, it sounds like computer vision is sort of a big component of what you have done. Is that true? Is that your passion, I guess? Is that the part of AI you really like to do?
Yes, I really am hooked on anything that's computer vision related. I like hardware too, but I also like the software, the algorithms that run on it. So I have a deep insight into both aspects of, because you end up needing both. Your image quality can affect the application in many cases. Some cases don't matter. You can just use a webcam depending on what you're doing. We're doing this animal sizing project with the most recent project I've been working on. We're using a depth camera. The quality of the image is very important for you to get the data, and also understanding how to synchronize the color depth images is essential in that case. So a hardware experience was invaluable. But I would say my biggest interest is in computer vision and more advanced algorithms that rely on neural networks.
You mentioned animal sizing. I mean, and are you trying to take a 2D image and try and figure out the 3-dimensionality of it, if that's even a word, 3-dimensionality?
Yeah. Well, so for rover robotics, one of the things I worked on was a monocular depth system where you got your stream coming in and you're converting in the depth map. That was like 2018 when it was really hot to do monocular depth. But I personally don't trust monocular depth enough. I think it's pretty dangerous. In 2018, I remember going to CVPR, and there were a series of presentations on, maybe it was 2019, super resolution, which is related to monocular depth. 7 of the 8 papers presented said, well, as we looked deeper and deeper, we realized they were just hallucinating features that weren't there. And so you have to be careful. And it's the same thing with monocular depth. It learns the training data really well. So we had one that seemed to work well outdoors. Brought it inside the office, complete garbage. Retrained it indoors, okay, it works. Take it to a part of the office it hasn't seen before, complete garbage. And how much data are you going to keep putting into it to figure out how it works? It's unnerving to think that your neural network, this is a saying that I use a lot. It works until it doesn't. Be ready for when it doesn't. And that is unnerving for, I'm sure, a lot of your clients as well.
So it sounds like it's very narrow, I guess. It's kind of like a narrow AI application.
This one, yeah.
And even in any type of depth perception realm, is that fair? Like, so we were talking to Cargill, this was years ago, but they wanted to basically provide a way for, there's a just basically a mound of grain that they wanted to drive by and point something at it and say, tell me how much is in there, right? Like, what's the volume of this thing? And right now, somebody needs to actually go up and survey it, right? Get all the way around it. And so, the thinking was with some of the new camera technology, even like the iPhone has allowed you to capture some of this and get some of this data. And there were third-party software solutions that we were looking at using, so we didn't need to reinvent the wheel. But it seemed like at the end of the day, it was all in the training. And you can't walk up to something that completely it's never seen before and point it at it and say, this is what it is. Even when you try and there's some stuff going on with room sizing, right? You can walk into a room, I think, and take a picture and it tries to map it out. But correct me if I'm wrong, because I don't know this space, enough with regards to sort of 3D imaging. But, is that even possible today without having a whole lot of data around the specific thing you're looking at?
I would say 3 years ago, and even 2 years ago, CVPR, there were people still claiming that was possible, believing it. And that was, I would say more than half people believe it. But today, I think a lot of people are like, we got to be really careful because we've been burned. And we know that as soon as you get outside of the training area, they have the fancy term distribution shift for it. Distribution shift happens all the time. And statistical analyses based on some validation data you've collected never works anywhere near as well as a few weeks of experience in the real world application, like we're deploying your application in the real world, where you see really how it fails and how often it fails. And even then, you know that there will be scenarios like, okay, now it's winter and everything looks different, or the weather is a little bit different now, nothing works.
Yeah, so it feels like we're in this era of AI right now, machine learning, whatever you want to say, but the data is very, very, it's not generalized enough. You're solving these little problems sort of one by one.
Yeah, well, I think the expectations for AI have shifted wildly back and forth. The AI winters are generally like the expectation for like, wow, we're going to have robots that can do anything. Human level intelligence is right around the corner, and then nothing changes, and then the expectations like, we're not going to invest in it, or it's never going to happen. And this is the closest we've come to generalizing the human ability for learned expectation. That's what we're doing here. And if you think about what toddlers have to do to get learned expectation to be able to not fall, if you wanted your toddler to be able to walk along, climb up on the sofa and walk and not fall, it's going to take about 2 years before you're still pretty nervous about them doing it.
Yeah, sure.
And that's a lot of data, and it's highly specific to your environment. And yeah, they're building multiple models in their head, and we don't have the ability to build these multiple models. There are people working on spatial perception where they're trying to tie these things together, but it is very challenging. And ultimately, I have a kind of contrarian view of AI with neural networks, more specifically, that goes deep to the nature of science. Like David Hume, the Scottish philosopher, who came up with the whole black swan problem, and the whole idea that you can't prove causality, which was kind of a shock to other people. And people enjoyed reading about that for a little while. Like it's true, you can't really prove that A causes B. All you know is that B follows A consistently.
Mm-hmm.
It's learned expectation. And for like Nassim Nicholas Taleb talked about this in his book, The Black Swan, that when the turkey wakes up every day, the sun comes up. Sun's going to come up tomorrow. And this is true until it isn't on Thanksgiving. It's a perfect little sizing down of the problem. Like, yeah, you're going to have an unexpected stuff that boils up on you, which we see every few years in macroeconomics. Our assumptions were true until they weren't. And then
right,
you adjust them.
Sure. Well, you probably just touched on it, as well. But I mean, one of the things I do like to ask people is how do they define artificial intelligence?
Yeah. So what's key to my understanding of it is the intersection between computational complexity. And it's like, how many steps does it take to compute an algorithm? And like polynomial versus exponential complexity. Computational equivalence. Most people call it like Turing completeness or computational power or even expressiveness of a system. And provability. Can you prove that something's true or not with logic? This is all balanced by the fact that all of the AI stuff and the way our brains work, these are all just approximations to the problems. They're not in the domain of logic where you're trying to brute force figure out exact solutions to things. But they're all running on computers that are running exact binary operations, and they're guaranteed to be exact. This generalization ability is in the domain of the provable or not. Can you prove that this is generalized or not? And ultimately, I wanted to raise something that is rarely learned in computer science or anywhere else in sciences. And I didn't understand it until fairly recent. And that's really our expectations of what reason is, reason or logic. If you have a collection of rules, like when you're thinking through something in your head, you think you're using reason this time and some approximations. And when computers are operating, they're always using reason or logical operations. Math is like applied logic, or where logic can go, and logical mathematical proofs are the basis of compilers and all computations. You write code in a certain way, and there's a proof for how that can be converted into a different representation and then another, like LLVM and compilers, when they're converting stuff back and forth, they're all based on simple proofs. Given this input, I can transform into some other world on this CPU. I transform into any of these.
Yeah, and it'll always be the same.
Yeah, it'll perform the same algorithm. The goal of math, by the end of like 1800s, they were making great strides in like figuring out stuff. By the end of the 1800s, like, we're going to link everything together so that everything is provable, and we're going to prove everything. And in 1931, that was completely blown apart by Kurt Gödel, this Austrian mathematician. It's a really cool proof that I had to read 6 times, other people's explanations of it 6 times to get it.
Yeah.
He used prime numbers to like represent operations, and these massive numbers was a theorem. And he basically said, this theorem is unprovable. And that conflicted with the goals of, or the setup of the system. And basically he proved that within any consistent system, there will be things you can't prove, whether you can't prove or prove that they're false or
Interesting.
disprove. And this blew the mathematicians' minds. And gradually became clear that there were more and more things that were in this domain of the unprovable. And it's clear to me that like neural networks are way in the domain of the unprovable if you think of them, no matter how you think of them. But approximations are even further into the domain of the unprovable. You're just never going to have certainty. Like with proteins, they're really complex things. Or SHA-256, secure hashes. Like Bitcoin SHA-256, SHA-2 with 256 bits, the basis of Bitcoin. Can you generate the same hash by tweaking something slightly in a message, or generating a completely different message and then hashing it? It's theoretically possible, but it's exponentially complex. You're going to run out of atoms and energy in the universe before you even get a measurable distance into that problem if you're trying to brute force it.
Right.
It's just so far into the unprovable that
Yeah.
if you've got all these practically unprovable, they may as well be unprovable. Like, yeah, you can form a logical argument that if you just kept running the algorithm for 10 universes, you'll get there. Like, well, that's never going to happen. So that's practically unprovable. And then there's the proved unprovable that is a lot of this stuff. And so we have to really balance how we build these solutions for our customers with the mind that you have to wrap something around your algorithm, right?
For sure.
Like, have you run into that in your experience? Like a lot of customers expect more out of these neural networks, or just any algorithmic solution. They might expect more than is realistic.
Oh yeah. No, with any new technology, you mentioned the AI winters and stuff. We definitely have seen that, at least collectively as an industry. I feel like over the past couple decades, where hey, this is the greatest thing since sliced bread, and it's going to solve all the world's problems. And I see a lot of that stuff with Internet of Things as I've been in that industry for the past decade. And then reality sets in, and it turns out that you're right. What a 2-year-old can do by not only standing up and walking and what they've learned, but like, hey, here's a bunch of pictures, like find the one that looks like a face, in there. And it's very abstract, arty stuff. And a computer cannot see that. But a kid's like, there it is right there. That's a face, And so it's those type of things that are just so simple for a human to do that computers still have a huge struggle doing. And people that aren't in this space, I feel like that maybe don't understand, I guess, how AI works, machine learning. They're like, well, why don't you just write another rule in there for it? And it's like, no, it doesn't work that way. Like, we're not programming systematically. Here are a bunch of if then else statements in here, right? The computer needs to actually be as smart as an intelligent brain is. And we need to train it through lots of mathematical, iterations. And you touched on something, I think, when you and I were sort of reconnecting here around the idea that, there's a lot of stuff that's not provable inside these neural nets. Right. And I think that scares a lot of people. I mean, when I have these conversations with a lot of people that are in the space, they're like, we don't know why it gets the result. It does get the result and it's correct, but we can't explain every hop that happens through the neurons of this neural network. And, I think you mentioned something to me like, do we have to? Maybe we don't need to, because it can perform well enough today. So should we care about what's going on internally?
Well, we definitely should care. There's definitely ways to improve our learned expectation of the neural networks. Like we have our experience, and that's what enables us to do stuff with it. We're building on shoulders of other people who have toiled on this for decades. The finding that you could use backpropagation with a small fraction of the gradients was a huge, like, oh, that actually works. That actually allows the neural network to adapt to it. And then I think 3 years ago, there was this fast AI paper about the first few iterations, you should actually let it get the full gradient through, and that'll let you converge faster in your training. But I think that's kind of, I don't know what, everyone uses different tricks and techniques that we basically learned how to train neural networks kind of the way that you train a toddler how to eat with a spoon, eat out of a spoon.
Yeah, right.
And it's like, it is messy and it's powerful though, because the end result is something we all want. We want to get that toddler to be able to eat and not choke.
Sure. But it's some of the creative aspects that I think are very difficult for neural networks to pick up. These ones that are part of the outliers, right? And even this idea of injecting random data. So it's not too perfect, in ways. Have you seen that be applied?
Yes. Some of the methods work I've done are, so I've done methods work on triplet loss, also very interesting, and injecting random noise at different layers of the networks. I never got anywhere with the injecting random noise. I've read a few papers on it, and I think it's potentially a very powerful way forward. Hopefully somebody will hit upon a way to really harness it. Maybe they have already, and we'll see it in a few weeks. The pruning is really interesting with, like, say, VGGNet was like the earliest ones. There's like 420 weights. And it was 2014, I think was the year that people started realizing that you could remove some weights, retrain it, and get pretty close to the same accuracy, ultimately, or on the validation data set, and get down to about 10% of the size and still have the same accuracy. And this group at NVIDIA did what's called oracle pruning, where, okay, if you're going to do pruning, it's going to take a long time. You have to pass all of ImageNet through it. It's going to take you, let's say you've got a beast of a computer, and it's going to take you a month to run all of your pruning experiments. And you're really just going to try a few pruning operations. You're not going to try, what happens if you prune all of the 420 different connections? And that's just VGG. There's bigger ones, certainly by far, with more potential connections. And they had access to thousands of GPUs at NVIDIA, and they did ORS pruning. They proved them all. And they found that it's hard to reason about. You could start anywhere and still get roughly the same benefit. You randomize the weights and you pass data through it. You can envision it as traversing space. Each weight moves somewhere. Your error surface changes as you move through this n-dimensional space. It's impossible to really think about, but it's fun to say space because you can approximate that linearly as well. I can move left to right and forward and backwards. That's easy to reason about. But you can start with any random weights and train it, and you'll have a completely different network. If you measure like a distance metric, like the L2 distance of all of your weights in neural network 1, 2, 3 through 1,000, they'll be all over the place, but they'll all be about as good, which is stunning. They will have shared features. They tend to have shared features, but there's no guarantee. Sometimes they'll seem to have the ability to detect certain features at certain neurons and other ones won't. And they'll have about the same accuracy. It's a collection of hierarchical rules we think is a useful way to think about it when you're training these. But that's about the best I think we can do right now.
Yeah, for sure. And I was just going to say, for people maybe that aren't into pruning, I guess, do you have a short definition of what that means?
Pruning means removing network connections so you don't have to compute them. You don't have to run the multiply add on that particular neuron, which can speed things up, especially on CPUs. GPUs, it's a lot harder to speed them up with pruning because it's already parallelized. So honestly, today, I don't think many people bother using pruning just because you don't get much of a speed up on GPUs.
Sure.
But if you need to use a CPU, pruning is very valuable. Basically, what you're doing is you might have a layer that has 32 channels. You could do away with a whole channel, or you could do away with specific filter weights on that channel, and then just avoid those computations. And in general, people were able to get rid of between 70 and 90% of the connections and still end up with a trained network. The trick is that you train it and then you start removing networks and retraining. But there's a bunch of different ways to get it, and there could be more discovered. But I think people have moved it. I don't think anybody's really focusing a lot of effort on it besides people who, that's my method, that's my area. I think mostly it's quantization and compression of neural network to try and speed them up on GPUs or accelerator chips.
Yeah, and you're doing a lot of stuff sort of at the edge, right? When you have these robots.
Yes. So whether you're using like an NVIDIA Nano that's got a GPU on it, 128 cores, the big challenge with the NVIDIA products is that and I don't know about the Xavier, I haven't had experience with that yet. All of the backends, like say in PyTorch, you'll have a 2 CUDA. And what that does is that calls the CUDA library to explicitly copy your network or your data over to your graphics card, which is a separate card, right? It's got its own memory. Well, not on the NVIDIA Nano or the TX1 or TX2. It's the same. They have shared memory. But for some crazy reason, they never went and the NVIDIA engineers are making these backend changes, there is a primitive that allows you to just copy in place or not actually do the copy. So you end up you waste half your memory on those particular plans. I don't know if that's actually changed. I should look around a little more careful, but I was doing some segmentation work on an NVIDIA Nano a month ago, and it was using an insane amount of memory. And I was like, let's hold off on this until later. But you can do some of these tasks on the CPU if the CPU is fast enough and you spend enough time figuring out how to do that. Like the Raspberry Pi 4, I have a almost real-time object detector running on 80 by 80 images. It's admittedly smaller, but it's just a standard MobileNet 3. I didn't even modify the network at all. This is just a quick get it working. What I had to do to get it working was I recompiled OpenBLAS. I used MXNet, even though nobody else uses anymore. And MXNet was great. It was the first one that was designed properly, and then PyTorch basically copied it, and now nobody uses MXNet. But it's still faster than PyTorch.
That's funny. Yeah, I was actually just looking at that recently because I had somebody on the program, and they were talking the same way that you were, like saying, "Oh, look, the MXNet's awesome." And I was like, "Whatever happened to that?" It's still sitting out there as an Apache open source project, right?
Amazon did not support it very well, and internal Amazon engineers don't even use it, which is really unfortunate because I thought that PyTorch 2.0 was going to redo the just-in-time compiler better, and they didn't. So it's still a little bit slower than MXNet. Anyways, by recompiling those with the right neon flags, you can do up to 8 multiple ads at the same time on the CPU. You can accelerate, and then on a single core of your quad-core CPU. I was able to get this object detector to run in 180 milliseconds. So I task locked one to CPU 0, another one to CPU 2, CPU 3, and then I would just send them messages I'm running at 25 frames per second. So I'm getting 50 milliseconds. So I'm sending them every 50 milliseconds, they're getting an image, and amortized, they get them just fast enough. I might drop a frame here and there, but it's practically real time with a bit of a delay.
Wow. Yeah, that's great. And you said running on a Pi 4?
Yeah, Raspberry Pi 4, which are now becoming available again.
Supply chain issues, I guess, all that stuff.
Yeah, so nanos are going to be hard to get for several more months because I think they're a 14 nanometer node. The 28 nanometer node is already oversupplied, which is what the Raspberry Pi 4 is on. So prepare for lots of $35 Raspberry Pi 4s again. But the Nano would be a while before they come out.
Yeah, well, you got me thinking about, so just, when you're running processes at the edge and you have the neural network already trained, you can easily get by with any old generic flavored CPU in a lot of these cases. Is that fair to say?
Yes, if you invest a little bit of engineering time into speed tests, make sure it runs fast. Because on the Nano and the other NVIDIA platforms, the time it takes to transfer the memory bandwidth over eats up a lot of your gains. I was getting object detectors running in 50 milliseconds. On the Raspberry Pi, I'm not that far off.
Right.
I'd like to see more.
Well, I also think about things that run on battery power. I mean, I would assume that you can run stuff a lot more low power mode on a CPU versus on a GPU or anything that NVIDIA is putting out, because they're pretty much built for dedicated power in a lot of ways.
Do you follow RISC-V?
No.
Oh, you're going to love this. So RISC-V is open source CPU architecture design. It's going to be a few years before the peripherals support, like all of the want to control video thing. And it's going to be a little while before it's fast enough and validated at smaller node sizes. But it will, within 10 years, I'm convinced that Intel will be making half of their processors with RISC-V rather than their own. They've already committed to making some processors with ARM, a direct competitor, and they've committed to making some with RISC-V, even though it's a little early for RISC-V. But it's just going to get better and better. And they've hired Chris Lattner, the LLVM guy, who then went on for Swift. He created Swift and did TensorFlow for Swift. And his focus is making sure that they can do massive SIMD instructions oriented specifically for neural networks. Because the specs are one thing, but actually running on a neural network, you can get very different throughput because of this complicated interplay of the memory bandwidth, your cache, your processor cache, your L1 and L2 cache, will completely change what you're actually going to get versus your expectations. And so having him on board, I'm expecting good things specifically for neural networks out of RISC-V within the next 5 years.
That's super cool. Yeah. So as a part of the program, we always have liner notes and stuff that we publish along. So I will make sure to put a link to RISC-V in the notes as people read through the transcription and want details of the podcast. That's a great source of information. So what tools are you using these days? It sounds like you're very much in the NVIDIA area. Do you use any stuff with TensorFlow, or is it all PyTorch, or like what are some libraries that you're leveraging?
PyTorch. I still use MXNet on my thermal cameras, but PyTorch for corporate development projects, just because I know that you can't rely on MXNet because it's being orphaned, unfortunately. I wish someone would take it up and champion it, or maybe it is going to be around longer. I really wish it would, because it is definitely faster and that saves cost all around. But so PyTorch, for the most part, I had to use TensorFlow for a while with that autism diagnostics company. But the selling point of PyTorch for me was that it's better than Caffe. And I was expecting TensorFlow 2.0 to exceed that.
And it didn't.
That's just my experience. But for me, the selling point of TensorFlow still today is that it's better than Caffe.
Yeah, right.
That's just my snarky look at it. It's fine. Lots of people use it, and they've done great things at getting TF Lite, TensorFlow Lite, to run on the edge.
Yeah.
Accelerators that run with it. So it's well supported, certainly. I tend towards PyTorch more just because I like it's almost identical to MXNet's philosophy. Procedural programming you can do with it.
Sure. Well, what's a day in the life of a person in your position in all these different roles and companies?
Planning, managing expectations, keeping corporate partners and teams on the same page, aligned. So there's lots of, not quite administrative work, I'd say more leadership, oversight role. And then when there's time, about half the day, if I'm lucky, spent on let's try to limit ourselves to a very specific small area of the computer vision algorithm or hardware, depending on what's needed at the moment. Set out what we want it to look like, what we know and what we don't know, and just try and figure out that one small area, document it so we can move on and not have to come back to it again. When I was younger, really up to 4 years ago, I suffered from the disease of the physicist programmer. It's quite common. Like, well, I'll just keep hacking away at the code until it works, right? And it's certainly gotten better over the years, making it more maintainable, but it wasn't until I really had an epiphany 4 years ago. It's like, I need to program better. I need to program in ways that I don't have to come back and revisit mistakes I made. Modularity, because it just eats you up. Maintenance of code. Fred Rooks and the Mythical Man Month. My God, that's still relevant today. Perfect. And it's kind of thing that, man, they don't teach these things in school because there just isn't enough time in the day. And you haven't faced the pain yet.
Yeah.
Entrepreneurship and learning anything in life. If the feedback is unclear, delayed, or ignorable, we don't learn anything. So if you're in a startup where you're not going to get feedback for a while, not learn. Or if you have unlimited amounts of money, you might not learn because you can just ignore consequences. And I've met people who haven't learned anything despite their startups. And there have been times I haven't learned things, but like Peter Thiel wrote this book, 0 to 1, or one of his students wrote it based on lecture notes, where he pointed out that most startup founders will tell you, well, we failed because of X or X and Y. And really they failed because of a dozen things they could have done better. And in my mind, your job is to figure out as many of those as you can so you don't make them next time.
Right. Yeah. I mean, that's, I think part of that's what it takes to be human, I guess, is to try and learn from your mistakes. And, what the definition of insanity is doing the same thing over and over again and hoping you'll have a different outcome, and so the more you can pick up and learn along the way, I guess, bringing it back to AI and machine learning, I guess, the better you'll be in the future. What's the size of teams that you're working with and sort of like the composition? Are you kind of working on your own little projects in sort of a team of one, or what's your experience in working with the group?
It's varied. Let's say Cognoa is on a team of 3 focused directly on AI and autism diagnostics. At Digilabs, I was the sole AI person, but I ran an AI, like how to do neural networks from NumPy and PyTorch, or Python.
Okay.
At Digilabs, just giving them my take on it and working through how you can look at the gradients flowing through it with NumPy. And at, Thermal Diagnostics, when the pandemic began, and I was like, I see all these fever screening solutions. They seem like a great way to reduce our risk, but I see all these stupid, crazy ways of doing it. Like they're forcing people to set up a black body, which is a known standard candle. It's glowing in the thermal domain, so you can't actually see it, but it's always coated with a black looking surface because it's engineered to be highly emissive, which skin is also highly emissive. They get out of skin. And it's standing on a tripod, but these are industrial calibrated. You knock that tripod over, you don't have a black body anymore. It's broken permanently. Like you can't drop a black body several inches without wondering it might be broken. And so I was like, this is crazy. Why don't you integrate the black body into the device itself and correct for air temperature and correct for distance to target and use a face detector? You make a much simpler, easier, foolproof application that doesn't require the customer to set up basically a laboratory experiment in their entryway.
Right. Yeah. Yeah.
I realized something unsavory, unfortunately. Turns out no one had figured out how to do it.
Oh, really?
I thought everyone was correcting for air temperature. Turns out not a single product even bothers measuring the air temperature. You go outside in the wintertime, your skin temperature is going to decrease, right?
Yeah, totally.
You go into a sauna, it's going to go up. The air temperature in an office is oscillating anywhere between, like, the best maintained might be only 2 degrees, might be 10 degrees. That is enough to turn like the best working system into something that has a false positive rate of 50% or worse. And that's just the 4 degrees allowed by the standard.
Sure.
And some buildings are worse. That's 50% false positive rate. So how do these things seem to never really detect anything? They never have a false positive. It's great, right?
Yeah, right. Everyone's safe.
They push the numbers towards normal so hard that they couldn't detect hypothermia or a severe fever.
Oh, crazy.
Most of them. There are some that just adhere to set up a lab in your entryway. And if there's any problems with the lab, it's on you, not us. And so that culminated because I was obsessed with it. I had to do a research study showing several comparisons of other studies. And I came up with a test method. I have a preprint that just went up on medRxiv, and it's under review at Journal Biomedical Optics. And this shows several clear problems with the way it's done today. And ultimately, the FDA needs to step in and say, okay, everybody stop. Let's do this correctly. And then let everybody start again. Because there are some companies that have been selling stuff for 20 years and getting away with something I agree with.
When the pandemic first hit, I mean, everyone was flooding the market with solutions. And
Yes.
Maybe like kind of what you're hinting at is there's no quality control on this. There's no standard. It's just, you can put out anything in some ways, right? I don't know what would stop a company, like you said, if they're already in the space, like, hey, let's just do a product that does this and sort of, but they don't have to prove anything. Is that true? It seems like
There is a standard, but it's entirely equipment based. And they don't even mention air temperature at all. I was like, they didn't realize that was a problem. It's just astounding. I'm sorry, I get quite passionate about it, but I'm putting that on the shelf because, well, the market is poisoned now. It's gone for several years.
Well, that's what's interesting about some of this technology or some of the algorithms, just these techniques. It feels like they can kind of come and go, right? You never really know when it's going to be the hot time. And I'm working on a startup, have been working on a startup for the past 2 years or so around presentation skills. So before the pandemic started, we're using AI to take a look at people's eyes. Are they looking at the camera as they're presenting? Facial expressions, right? Are they happy, sad? So giving back visual cues to the person. But then we're also doing a lot of stuff with audio. So, if you can present better by saying not so many ums and ahs, if you can just slow your speech down a little bit. And so kind of bringing that together into a virtual coach. But, we started this before the pandemic and we had this really difficult time. Like, how are we going to get all this video and all this audio when someone's at the podium, right? So like someone's got to sit there with their phone, and we were going down all these paths of like building a mobile app to capture all of this. And then overnight, when the pandemic hit, everyone got on Zoom. And we're like, ta-da. It was actually kind of make lemonade out of lemons in a way, because now all of a sudden you and I are in these meetings and everyone's in these virtual meetings and my face is here front and center and the audio is really good. You can hear everything. And so, it was just kind of one of these things where the market changed in our favor. Now, a lot of other people are doing the same thing. So it's not like we had the corner of the market, but it was amazing that because of COVID, now all of a sudden everyone went online, and this piece of this technology and this startup that we're working on now seems very, very relevant when it was very difficult to not get the data or hard to get the data, right? That's one thing I think that's sort of changed now is this idea that, at least in our world, everyone's in front of the screen, but also everyone's at home, and Netflix is getting a lot more subscribers. I mean, it's just this whole digital world feels like there's just a lot more data we're giving away today.
Your application now has data that you don't have to really struggle and fight for like a lot of startups do.
Yeah. So sometimes, you can just, outside market forces can completely change it. So I totally get it. Put your thing on the shelf and we'll see where it goes in the future. One of the things that I like to ask people is if you were entering the field today, so rewind the clock back, you took an interesting path to where you got to where you are today. But if someone's getting out of school, and like, what are things that you might suggest? You mentioned a ton of books here, and I'll be sure to put those because they're all very good, standards, Mythical Man Month and others. And I'll list those in the notes. But yeah, if someone's coming out of school and they want to get into this artificial intelligence, machine learning, CV sort of space, what do you advise that they do?
I would say it depends on what areas they want to contribute in. And it's hard to tell because your desires will change as you get exposed to different areas. So definitely get exposed to different areas in it. But if you want to do anything with orchestration of these things, or even orchestrating your own working environment, it really pays to know Linux better. Just like how RISC-V is going to take over the chips industry, Linux has taken over the computing industry, or the POSIX type operating systems, where they all share the Unix-like environment, even Macs. Like Microsoft now runs over half their cloud runs Linux. I would say Linux from scratch is invaluable. It teaches Bash scripting. Python scripting is also is a clear requirement for this field nowadays. Definitely learn some better programming practices, how to make code more modular, while realizing that's well in the domain of the unprovable. You can never prove that your code is perfectly modular. There's an infinite number of ways you could redesign, but stopping and thinking about the design, really sketching out carefully what you want your inputs. Programming on paper is the most valuable programming you will do. For me, I have to do on paper. It prevents me from starting coding until I'm really ready.
I love that. Yeah, that made me think of back in the old days with index cards or whatever, when people would run stuff on the mainframe, right? It would force you to actually think through your program, right? Because it was like the next time you were going to get a chance to run it might be 12 hours later or a whole day later, right? And so you really needed, it wasn't like a just, control, R and just recompile the thing, right? You needed to make sure. And so people would really, really double check and triple check all of their stuff before they ran it through.
Constraints are your greatest friend.
Yes.
Learn to love constraints. Find them. Build more in if you can. Well,
Sure. Good programming practice. I think object-oriented design, by Booch and others, they're really good. Books by Gang of Four. These are things that I came to later in my career because I was kind of a little bit of a cowboy coder at the beginning, and then I started working with other developers and I started seeing patterns emerge, and I'm like, what is this all about? And started stepping back and realizing, oh my gosh, yeah, there's general programming principles that you can do that you can put in today that will help you create more flexible code in the future. So I think that's kind of what you're getting at.
Yeah, like Git flow. Learn Git flow if that makes sense for your group or your team. I did that for a good year and a half with one group. Another group, it was more just we split off into modular sections of the code. If the underlying architecture designed modularly, then it can make a lot of sense to split off into different parts of it. But you still have to align on how everything's going to talk together.
For sure. Yeah, that's where I think software is a little bit more of an art than it is of just a straight science or just procedural.
One of the things I touched on earlier, talking about logic and provability and all that, I wish more people were just aware that there was a paper 15 years ago about why most published papers or most medical studies are false. John Ioannidis published that. And it's true, most published papers, published work is non-predictive. They're publishing a mirage. That's not because the scientists are unethical or incompetent. For the most part, there are certainly some sociopaths amongst the scientists, less than 10%, I'd say. I worked at a hospital. I worked with a fair number of really intense, scary people. So yeah, definitely psychopaths who then stole work that we've done. And for the most part, you're trying to get funding. You're trying to find a way forward on something. Let's say we're studying multiple sclerosis and we're looking at lesion volumes in the brain and trying to understand, is there a way we can predict the course of disease if it's going to convert to a different type? So a drug trial, so we know each time you look at the data, you have a chance of finding something that's a mirage. That means if you look at the data 10 times, let's reanalyze or let's reprocess, let's clean the data up a little bit better and we'll look at it again by applying a slightly different analysis. You've just doubled your chances of finding a mirage that isn't real, but still fits that, hey, the correlation was significant or the fit was significant after we took out all the confounds. And that is still to this day the most common cause of this. And there are people who are aware of this in the field and like, well, I have to publish this because it's promising. And I've taken as much care as I can to justify and limit the number of times to reprocess the data. But that's why most of them are false. And it's just going to keep on happening. And there's gold in there, but it's hard to find. And if it was easy, we'd already have it. And
Right.
a lot of this stuff is unprovable, and it's gonna remain so, which means we have work to do, and we will always have work to do.
Makes it good for scientists, I guess, people that are in this field, for sure.
I'll look for the silver lining. There's work for all of us. There will always be more to do.
Yeah.
We can be busy forever.
Well, good, Erik. I appreciate your time today. Before we end here, how do people get a hold of you? Just, I think you're on LinkedIn, right? Is that probably the best place?
Yeah, that's the best way to get a hold of me, I'd say.
Excellent.
LinkedIn is fantastic nowadays for communicating in this domain for business opportunities, or just, it's like a great networking site. And I don't use Facebook anymore. I've been using that for 10 years. More and more people.
There's a lot of people. Yeah, for sure. Was there anything else that I maybe missed that you wanted to share?
Oh, I could talk for hours on various things, medical devices and things that I think are suspicious in that area, but I don't want to get sued. So we'll leave that for private conversation.
Sure. Understood. I'll put a link to your LinkedIn profile here in the liner notes here. And I just, again, appreciate all of the time that you gave us today and your input. And, you got your hands in a bunch of different stuff over a number of decades here. So excited to see where you go in the future and how artificial intelligence and machine learning plays into that. Sounds like it's going to be a big component. Wish you nothing but the best, but can have you maybe back on the program next year or so, and we'll touch base.
That sounds great. Thank you so much for having me, Justin, and have a great rest of your day.
You've listened to another episode of the Conversations on Applied AI podcast. We hope you are eager to learn more about applying artificial intelligence and deep learning within your organization. You can visit us at appliedai.mn to keep up to date on our events and connect with our amazing community. Please don't hesitate to reach out to Justin at appliedai.mn if you are interested in participating in a future episode. Thank you for listening.